Iron is a chemical element with symbol Fe and atomic number 26. It is a metal in the first transition series. It is by mass the most common element on Earth, forming much of Earth's outer and inner core. It is the fourth most common element in the Earth's crust. Its abundance in rocky planets like Earth is due to its abundant production by fusion in high-mass stars, where the production of nickel-56 is the last nuclear fusion reaction that is exothermic. Consequently, radioactive nickel is the last element to be produced before the violent collapse of a supernova scatters precursor radionuclide of iron into space. Like other group 8 elements, iron exists in a wide range of oxidation states, -2 to +6, although +2 and +3 are the most common. Elemental iron occurs in meteoroids and other low-oxygen environments, but is reactive to oxygen and water. Fresh iron surfaces appear lustrous silvery gray, but oxidize in normal air to give hydrated iron oxides, commonly known as rust. Unlike many other metals which form passivating oxide layers, iron oxides occupy more volume than the metal and thus flake off, exposing fresh surfaces for corrosion. Pure iron is relatively soft but is unobtainable by smelting. The material is significantly hardened and strengthened by impurities, in particular carbon, from the smelting process. A certain proportion of carbon produces steel, which may be up to 1,000 times harder than pure iron. Crude iron metal is produced in blast furnaces, where ore is reduced by coke to pig iron, which has a high carbon content. Further refinement with oxygen reduces the carbon content to the correct proportion to make steel. Steels and low-carbon iron alloys along with other metals are by far the most common metals in industrial use. Due to their great range of desirable properties and the widespread abundance of ion-bearing rock, iron chemical compounds have many uses. Iron oxide mixed with aluminium powder can be ignited to create a thermite reaction, used in welding and purifying ores. Iron forms binary compounds with the halogens and the chalcogens. Among its organometallic compounds is ferrocene, the first sandwich compound discovered. Iron plays an important role in biology, forming complexes with molecular oxygen in hemoglobin and myoglobin. These two compounds are common oxygen transport proteins in vertebrates. Iron is also the metal at the active site of many important redox enzymes dealing with cellular respiration and oxidation and reduction in plants and animals. Characteristics. Mechanical properties. The mechanical properties of iron and its alloys can be evaluated using a variety of tests, including the Brinell test, Rockwell test and the Vickers hardness test. The data on iron is so consistent that it is often used to calibrate measurements or to compare tests. However, the mechanical properties of iron are significantly affected by the sample's purity. For research purpose, single crystals of iron are actually softer than aluminium, and the purest industrially produced iron has a hardness of 20 to 30 Brinell. An increase in the carbon content of the iron will initially cause a significant corresponding increase in the iron's hardness and tensile strength. Maximum hardness of 65 Rc is achieved with a 0.6% carbon content, although this produces a metal with a low tensile strength, because of its significance for planetary cores. The physical properties of iron at high pressures and temperatures have also been studied extensively. The form of iron that is stable under standard conditions can be subjected to pressures up to California 15 gigapascals before transforming into a high-pressure form, as described in the next section. Phase diagram. An allotropes iron represents an example of allotropy in a metal. There are at least 4 allotropic forms of iron, known as alpha, gamma, delta, and epsilon, at very high pressures. Some controversial experimental evidence exists for a phase beta stable at very high pressures and temperatures. As molten iron cools, it crystallizes at 1538 degrees Celsius into its delta allotrope, which has a body-centered cubic crystal structure. As it cools further to 1394 degrees Celsius, it changes to its gamma iron allotrope, a face-centered cubic crystal structure, or austenite. At 912 degrees Celsius and below, the crystal structure again becomes the BCC alpha iron allotrope, or ferrite. Finally, at 770 degrees Celsius, iron becomes magnetic. As the iron passes through the Curie temperature, there is no change in crystalline structure, but there is a change in domain structure, where each domain contains iron atoms with a particular electronic spin. In unmagnetized iron, all the electronic spins of the atoms within one domain are in the same direction. However, the neighboring domains point in various other directions, and thus overall they cancel each other out. As a result, the iron is unmagnetized. In magnetized iron, the electronic spins of all the domains are aligned, so that the magnetic effects of neighboring domains reinforce each other. Although each domain contains billions of atoms, they are very small, about 10 micrometers across. At pressures above approximately 10 gigapascals and temperatures of a few hundred Kelvin or less, alpha iron changes into a hexagonal close-packed structure, which is also known as epsilon iron. The higher temperature gamma phase also changes into epsilon iron, but does so at higher pressure. The beta phase, if it exists, would appear at pressures of at least 50 gigapascals and temperatures of at least 1500 K. It has been thought to have an orthorhombic or a double HCP structure. Iron is of greatest importance when mixed with certain other metals and with carbon to form steels. There are many types of steels, all with different properties, and an understanding of the properties of the allotropes of iron is key to the manufacture of good quality steels. Alpha iron, also known as ferrite, is the most stable form of iron at normal temperatures. It is a fairly soft metal that can dissolve only a small concentration of carbon. Above 912 degrees Celsius and up to 1400 degrees Celsius, alpha iron undergoes a phase transition from BCC to the FCC configuration of gamma iron, also called austenite. This is similarly soft and metallic but can dissolve considerably more carbon. This form of iron is used in the type of stainless steel used for making cutlery, and hospital and food service equipment. The high-pressure phases of iron are important as end-member models for the solid parts of planetary cores. The inner core of the Earth is generally assumed to consist essentially of an iron-nickel alloy with epsilon structure. The melting point of iron is experimentally well defined for pressures up to approximately 50 gigapascals. For higher pressures, different studies placed the gamma-epsilon liquid triple point at pressures differing by tens of gigapascals and yielded differences of more than 1000 K for the melting point. Generally speaking, molecular dynamics computer simulations of iron melting and shock wave experiments suggest higher melting points and a much steeper slope of the melting curve than static experiments carried out in diamond anvil cells. Isotopes. Naturally occurring iron consists of 4 stable isotopes: 5.845% of 54 Fe, 91.754% of 56 Fe, 2.119% of 57 Fe, and 0.282% of 58 Fe. Of these stable isotopes, only 57 Fe has a nuclear spin. The nuclide 54 Fe is predicted to undergo double beta decay, but this process had never been observed experimentally for these nuclei, and only the lower limit on the half-life was established. T1/2 greater than 3.1 times 1022 years. 60 Fe is an extinct radionuclide of long half-life. It is not found on Earth, but its ultimate decay product is the stable nuclide nickel-60. Much of the past work on measuring the isotopic composition of Fe has focused on determining 60 Fe variations due to processes accompanying nucleosynthesis and ore formation. In the last decade, however, advances in mass spectrometry technology have allowed the detection and quantification of naturally occurring variations in the ratios of the stable isotopes of iron. Much of this work has been driven by the Earth and planetary science communities, although applications to biological and industrial systems are beginning to emerge. The most abundant iron isotope 56 Fe is of particular interest to nuclear scientists as it represents the most common endpoint of nucleosynthesis. It is often cited, falsely, as the isotope of highest binding energy, a distinction which actually belongs to nickel-62, since 56 Ni is easily produced from lighter nuclei in the alpha process in nuclear reactions in supernovae. Nickel-56 is the endpoint of fusion chains inside extremely massive stars, since addition of another alpha particle would result in zinc-60, which requires a great deal more energy. This nickel-56, which has a half-life of about 6 days, is therefore made in quantity in these stars, but soon decays by 2 successive positron emissions within supernova decay products in the supernova remnant gas cloud. First to radioactive cobalt-56, and then stable iron-56. This last nuclide is therefore common in the universe, relative to other stable metals of approximately the same atomic weight. In phases of the meteorites Samarkand and Chervony cut a correlation between the concentration of 60 Ni, the daughter product of 60 Fe, and the abundance of the stable iron isotopes could be found, which is evidence for the existence of 60 Fe at the time of formation of the solar system. Possibly the energy released by the decay of 60 Fe contributed, together with the energy released by decay of the radionuclide 26 Al, to the remelting and differentiation of asteroids after their formation 4.6 billion years ago. The abundance of 60 Ni present in extraterrestrial material may also provide further insight into the origin of the solar system and its early history. Nuclei of iron atoms have some of the highest binding energies per nucleon, surpassed only by the nickel isotope 62 Ni. This is formed by nuclear fusion in stars, although a further tiny energy gain could be extracted by synthesizing 62 Ni. Conditions in stars are unsuitable for this process to be favored. Elemental distribution on Earth greatly favors iron over nickel, and also presumably in supernova element production. Iron-56 is the heaviest stable isotope produced by the alpha process in stellar nucleosynthesis. Elements heavier than iron and nickel require a supernova for their formation. Iron is the most abundant element in the core of red giants, and is the most abundant metal in iron meteorites and in the dense metal cores of planets such as Earth. Nucleosynthesis iron is created by extremely large stars with extremely hot cores through the silicon burning process. It is the heaviest stable element to be produced in this manner. The process starts with the second largest stable nucleus created by silicon burning, which is calcium. One stable nucleus of calcium fuses with one helium nucleus, creating unstable titanium. Before the titanium decays, it can fuse with another helium nucleus, creating unstable chromium. Before the chromium decays, it can fuse with another helium nucleus, creating unstable iron. Before the iron decays, it can fuse with another helium nucleus, creating unstable nickel-56. Any further fusion of nickel-56 consumes energy instead of producing energy, so after the production of nickel-56, the star does not produce the energy necessary to keep the core from collapsing. Eventually, the nickel-56 decays to unstable cobalt-56, which in turn decays to stable iron-56. When the core of the star collapses, it creates a supernova. Supernovas also create additional forms of stable iron via the R process. Occurrence. Planetary occurrence. Iron is the sixth most abundant element in the universe, and the most common refractory element. It is formed as the final exothermic stage of stellar nucleosynthesis, by silicon fusion in massive stars. Metallic or native iron is rarely found on the surface of the Earth because it tends to oxidize, but its oxides are pervasive and represent the primary ores, while it makes up about 5% of the Earth's crust. Both the Earth's inner and outer core are believed to consist largely of an iron-nickel alloy constituting 35% of the mass of the Earth as a whole. Iron is consequently the most abundant element on Earth, but only the fourth most abundant element in the Earth's crust. Most of the iron in the crust is found combined with oxygen as iron oxide minerals such as hematite and magnetite. Large deposits of iron are found in banded iron formations. The banded iron formations were laid down in the time between 3,700 million years ago and 1,800 million years ago. About 1 in 20 meteorites consist of the unique iron-nickel minerals tannite and carmesite. Although rare, iron meteorites are the main form of natural metallic iron on the Earth's surface. The red color of the surface of Mars is derived from an iron oxide-rich regolith. This has been proven by Mossbauer spectroscopy. Stocks in use in society. According to the International Resource Panel's Metal Stocks in Society report, the global stock of iron in use in society is 2,200 kilograms per capita. Much of this is in more developed countries rather than less developed countries. Chemistry and compounds. Iron forms compounds mainly in the +2 and +3 oxidation states. Traditionally, iron compounds are called ferrous, and iron compounds ferric. Iron also occurs in higher oxidation states, an example being the purple potassium ferrate, which contains iron in its +6 oxidation state. Iron is a common intermediate in many biochemical oxidation reactions. Numerous organometallic compounds contain formal oxidation states of +1, 0, -1, or even -2. The oxidation states and other bonding properties are often assessed using the technique of Mossbauer spectroscopy. There are also many mixed valence compounds that contain both iron and iron centers, such as magnetite and Prussian blue 3. The latter is used as the traditional blue in blueprints. The iron compounds produced on the largest scale in industry are iron sulfate and iron chloride. The former is one of the most readily available sources of iron, but is less stable to aerial oxidation than Moore's salt 2Fe26H2O. Iron compounds tend to be oxidized to iron compounds in the air. Unlike many other metals, iron does not form amalgams with mercury. As a result, mercury is traded in standardized 76-pound flasks made of iron. Binary compounds. Iron reacts with oxygen in the air to form various oxide and hydroxide compounds. The most common are iron oxide and iron oxide. Iron oxide also exists, though it is unstable at room temperature. These oxides are the principal ores for the production of iron. They are also used in the production of ferrites, useful magnetic storage media in computers, and pigments. The best-known sulfide is iron pyrite, also known as fool's gold owing to its golden luster. The binary ferrous and ferric halides are well known, with the exception of ferric iodide. The ferrous halides typically arise from treating iron metal with the corresponding binary halogen acid to give the corresponding hydrated salts. Fe plus 2HXFeX2 plus H2. Iron reacts with fluorine, chlorine, and bromine to give the corresponding ferric halides, ferric chloride being the most common. 2Fe plus 3X2 2FeX3. Coordination and organometallic compounds. Several cyanide complexes are known. The most famous example is Prussian blue 3. Potassium ferrocyanide and potassium ferrocyanide are also known. The formation of Prussian blue upon reaction with iron and iron respectively forms the basis of a wet chemical test. Prussian blue is also used as an antidote for thallium and radioactive cesium poisoning. Prussian blue can be used in laundry bluing to correct the yellowish tint left by ferrous salts in water. Several carbonyl compounds of iron are known. The premier iron compound is iron pentacarbonyl, Fe5, which is used to produce carbonyl iron powder, a highly reactive form of metallic iron. Thermolysis of iron pentacarbonyl gives the trinuclear cluster, tri-iron dodecacarbonyl. Coleman's reagent, disodium tetracarbonyl ferrate, is a useful reagent for organic chemistry. It contains iron in the -2 oxidation state. Cyclopentadienyl iron dicarbonyl dimer contains iron in the rare +1 oxidation state. Ferrocene is an extremely stable complex. The first sandwich compound, it contains an iron center with 2 cyclopentadienyl ligands bonded through all 10 carbon atoms. This arrangement was a shocking novelty when it was first discovered, but the discovery of ferrocene has led to a new branch of organometallic chemistry. Ferrocene itself can be used as the backbone of a ligand, e.g., DPPF. Ferrocene can itself be oxidized to the ferrocenium cation. The ferrocene-ferrocenium couple is often used as a reference in electrochemistry.